is RPG.
So I will talk about feedback and multiphase condensation in CGM as well as ICM. So I will first start with how to incorporate cosmological accretion of gas in halos in the standard hydro simulations or hydro modeling of gas. And then I'll also talk about multiphase condensation in CGM motivated by the kind of things we see in ICM due to thermal instability. I work with Pratik, and I'll also thank Guinevere Kaufman and Elliot Quartert for a lot of discussions on these things. To begin with, I'll start with this nice movie. This is just n-body simulation, which only takes into account the gravitational processes, and we'll see how the dark matter halo is formed. So on an average, starting from tiny density perturbations, these perturbations grow until there is an equilibrium set by the random motion of the particles and gravity. So that's how this is kind of the end state of this kind of evolution, and this is how the dark matter halo is formed. So what happens to gas in such halos? First of all, gas starts following the dark matter potential, and so there are two kinds of accretion modes. One is where the gas falls in, gets shock heated, forms a visual shock, and then forms a quasi-hydrostatic equilibrium, which is a hot atmosphere. And in very small halos, which is roughly around 10 to the power 12 solar mass, sometimes this gas doesn't go through the shock and directly falls to the disk. So that is also known as the cold mode accretion. Yeah. So in the centers, in the central regions of the halo, the gas is primarily decoupled from how the dark matter potential evolved, because there is also gas physics and radiative processes. So the gas starts cooling inside out, starts contracting, and now it's audible. In the central region, gas cools and contracts, and this cooling is primarily regulated by the feedback due to supernova and radiant. So these are the two most important feedback modes discussed. And as we are listening to a lot of talks from yesterday, so these feedback processes, these throw away a lot of gas from the central regions, from the halos, and particularly the lower mass halos where we see a lot of variance missing. In the ICM, in the clusters, this effect is not that predominant, but in the smaller mass halos in CGM, it's very much a lot of gas, almost more than 50% of the gas is missing, of the variance is missing. So can we estimate in a very simple way how much variance are missing from the halos, and also the feedback power that is required for different halos? So we consider a semi-cosmological setup. For this, we do not take into account all the merger effects or the details of the n-body simulations. So what is done here is this is done from a Millennium n-body simulation. So you take the halos at the current redshift and you trace back the constituents in the previous redshift, and you see the most massive progenitor of that halo, and you say that on an average, so you trace back the most massive progenitor till some redshift of your interest, and you say that on an average the halo is growing like that. So it's basically a smooth, or the average growth of each halo. So the parameter of such a process is the current mass in the current redshift, and so these are the 4 cases of 4 current masses, and this is a smooth growth. So of course this doesn't take into account the merger history of the halos, but it's capturing the essential physics when it comes to individual halos like clusters or even groups and smaller galaxies. So first, just to have a simple model, we consider concentric shells, and so this shells evolve in the Lagrangian framework, and the outer shells, we start with a small halo, and the outer shells are going out with the Hubble velocity, and in the central region things are falling with due to the potential well in the center, and the potential well is gradually becoming deeper and deeper with time. So the halo is growing with time in mass and length scale, and in such a evolution can be seen by this. So these are the evolution of radial distance with time. So as time progresses, there is a shock formed. This is the visual shock. So shells are first moving out, then they're falling in, going through the shock, and then becoming almost parallel, which is like quasi-hydrostatic equilibrium. And if we so this arrow shows the virial radius with time, which is roughly around R200, corresponding to the halo. And in such a setup, we first start putting very simple cooling and heating prescriptions. So cooling is only inside the virial radius, and we start with zero metallicity cooling. And for heating, we use a hot Bondi accretion model. And so for this, we have this accretion efficiency and the heating radius. So we put heating only within certain radius. So these are our two parameters, and we need to constrain it so that it matches some observations. So a very good way to do that is abundance matching. So in galaxy formation theory, this plot is very popular because people take the stellar mass data from observations, and by abundance matching, they try to find the halo masses from mass functions in different n-body simulations. And this trend is seen in for different redshifts. So what we do is we take two redshifts, which is z equal to 0 and 1, and we first try to see how just cooling case works for different halos. So the biggest circle is the biggest halo, as shown in my first smooth mass accretion history profile, and the smallest one is the smallest halo. So all these have current masses. The smallest one has 5 into 10 to the power 11 solar mass. The biggest one has 5 into 10 to the power 14 solar mass. And we see that there is excess cold mass in these halos when there is just cooling. So we try to tune our parameters such that we match the total cold gas mass in the central region, as and all of them falls on these stellar mass halo mass trend. And this is how we take the runs, we fix the parameters for each run. And with this, we see the feedback power for each case. So the red one is the biggest halo, the black one is the smallest, and we see initially there are two peaks in both the bigger mass halos, which are 5 into 10 to the power 14 and 5 into 10 to the power 13. And the smaller ones, the smallest one is relatively very smooth, it doesn't show any peaks. For now, we can, so what we try to do is we try to see what fraction of this can be provided by AGN and what fraction can be provided by supernova. So what we do is we know the total cold gas in the central region. We use the Krupa IMF function and try to see how many stars are formed above 8 solar mass. And we calculate the total supernova energy per unit time. And this dashed lines correspond to each halo. So the red dashed line correspond to the first halo, and accordingly. So this basically means that these dashed lines for the biggest halos are there in the initial, say, around 1 to 4 gigayear, which means after that there is not much supernova feedback available for these halos. So it's essential to have some kind of feedback from AGMs. On the contrary, the smallest halos, for example, the black one, the dashed lines are almost always above the black lines, which means that supernova can provide almost the entire energy that is required for these kind of smaller halos. So with this kind of feedback, we try to see the baryon fraction within R200, within the visual radius. And we see that, so the red one is the biggest halo, where we see some kind of cycles coming up, where the cycle time periods are becoming smaller and smaller with in the current closer to the current redshift. And the smallest one, which is the yellow, it has a lot of variance missing for most of the time. So what happens is there is a feedback event initially. It throws away most of the gas, and that gas never takes a lot of time to come back inside the halo. And by the time we come to the current redshift, it's trying to recover, but there is not enough gas flowing in. So there is a lot of variance missing in this smallest halo. And this is kind of this is qualitatively similar to what is seen usually in observations. So in this plot, we see the trend between the total baryon mass in halos and the baryon fraction, and we see that the smallest baryon mass, which correspond to the smallest halos, they have almost the entire variance missing. And as we go to larger and larger in the cluster scale, kind of, so there a lot of variance are intact, present within the halos. So basically, lower mass halos do not have a lot of variance. Severely, they are lacking variance severely. But then in the COS observations, they do see a lot of cold gas in the outskirts, up to 200 kpc. So probably a lot of variants are existing in the outskirts of these lower mass halos. But then there is another question, which is how does this gas cool? Of course, one mechanism which has been discussed right from yesterday is that the hot wind is carrying cold. There is a coexistence of hot and cold clouds, hot wind and cold clouds. And as Pengo described, that if the cloud crashing time is longer than the cooling time of the warm gas, then there will be cold gas formation. So this basically talks about the survival of cold gas in the hot winds. We are trying to think of some other way of having cold clumps in situ in the outskirts, and we take some clue from Pratik's ICM simulations. So this is the 2012 paper which talks about the T cool by TFF around 10 condition for getting multiphase condensation. So this takes into account NMW potential and gas in hydrostatic equilibrium in that potential, and they start with tiny density perturbations which grow and cool down to around 10 to the power 4 Kelvin if the T cool by TFF ratio is around 10. So we try to take into account this kind of cooling mechanisms even in CGM. And we think of large density perturbations and the sources of large density perturbations. One is, of course, the cold mode accretion, the one I started with. So a lot of in halos which have masses lower than 10 to the power 12 solar mass, a lot of gas directly fall into the disk due to cold mode accretion. So these can provide large cold clumps in the halos, particularly in the outskirts. So one source is this. One source of large density perturbation is this. Another is the merger. So right now there is a good evidence that mergers can trigger some cooling in the outskirts. So there is this galaxy Malin 1, which is a Milky Way sized galaxy, and which has a stellar disk of going up to 100 kpc and has a steady growth of cold gas in such a disk. And standard galaxy formation theories do not really predict existence of such galactic disks. So very recently in the illustrious TNG simulation, they have found an analog of this kind of galaxy, which has a diameter of around 250 kpc, and they see that two minor merger events are trying to supply this cold gas steadily into the disk. So what they see is a 250 kpc diameter of disk in the current redshift, and they press back this cold gas right up to z equal to zero point 0.5, and they see that this is provided by two tiny galaxies coming in and merging with that galaxy. So mergers can provide can trigger growth of cooling in the outskirts. So with this idea, we try to take a setup very similar to what Pratik had. So this is a model which is where at first at T equal to 0 gas is in thermal and hydrostatic equilibrium, and with each time what we do is we see how much cooling is happening in each shell, and we put average amount of heating in each shell, so that on an average the shell is in thermal balance, but in tiny patches within the shell there could be more cooling or there could be more heating. So we begin with this kind of initial conditions, where the right one is the conventional setup that they started with in the ICM, and the left one has a lot very large perturbations in density. And we discover something else as well, that so these curves correspond to it's a parameter space. So the x-axis is the density perturbation delta rho by rho, and the y-axis is the T cool by TF. TTI is a factor of TTI differs from T cool by a factor. So y-axis is essentially T cool by TFF, and we see that as we go towards larger and larger density perturbations, essentially cooling happens without cooling is decoupled from the effect of mean T cool by TFF. So basically everything, all the space below this curve shows multiphase condensation. Space above this curve doesn't show. So as we go to larger density perturbations, essentially it's very steep, and mean T cool by TFF doesn't really have any effect. No matter how high the T cool by TFF is, we see multiphase condensation. So what we do is we take some slightly more realistic conditions where assuming that such large density perturbations won't be present throughout the ICM. So we take local patches of large density perturbation and we change the location as well, just to see the effect. We see the same effect in including bubbles, so we have different physical conditions under which we test this curve, bubbles and jets as well. Additionally, we also see the effect of entropy. So this is from Pratik's paper in 2012, where this is a number density plot, but as we go to this smaller and smaller density profiles, these have a more constant entropy in the center. Like entropy gradient is lower and lower in such systems. So basically, we want to see the effect of this constant entropy gradient where the core becomes larger, and this kind of is similar to the CGM in lower mass halos. So we also take a system where a medium where the entropy is completely constant, and we also take a medium where there is very large entropy gradient, and with all these effects we try to see the same condensation curve. So the solid line is same as the previous one with slightly different potential wells. We include a central galaxy potential BCG. There are these round points where the brown round points correspond to large density perturbations in the outskirts. The pink round points correspond to the large density perturbations in the central region, closer to the center. And we see that it's easier to get cold gas when the density perturbations are more closer to center, where entropy is really flat. So these are these uh, ping points. So basically, the threshold T cool by TSS is 15. So you come this side, you get cold gas. You go that side, you don't get cold gas. So this is easier here. Well, on the contrary, as we move out, it's more and more following the background curve. As those are these brown points. And as we move out, our entropy gradient is also is larger. So basically, that kind of verifies what Mark has been trying to say for a long time, and entropy gradient does prevent the growth of perturbations. Additionally, this also gives us clue to try a similar setup in the CGM. So in the CGM, as I said in the previous plot, the core is larger and the entropy is more or less constant till a very large radius. And so what we do is we take a setup where the entropy is constant entirely for the entire system, and these are these gray squares in the top, which have a significantly higher threshold. It is close to 15, and that means that it's easier to get cold gas when the entropy is constant, when there is no entropy gradient in the system. Then there are these black and lime green points, which have a lot of which have higher entropy gradients, and these are a bit more difficult. So these are coming this side, which means if you go to this side of the parameter space, then you get condensation. Otherwise, you'll not get condensation. Additionally, there is another interesting thing is that just like the previous condensation curve, so once you go beyond certain number like 1, delta rho by rho 1, you see that there is no effect of T cool by TFS. You essentially get condensation no matter what. Uh, Up to 30, 35, 40, I saw till some extent. So there is cold gas no matter what T cool by TSS you have in the background. So basically, with large density perturbation, you do not need to worry about T cool by TSS at all. So our prediction is that uh, this region, which has tiny density perturbations, which needs a hot medium, is basically ICM, where there is hydrostatic equilibrium, and it is primarily made of hot gas. On the contrary, CGM has a lot of cold mode accretion, and there is a possibility of large density perturbations in the CGM, where T cool by TSS essentially loses its meaning, and there will be cold gas condensation and multiphase condensation even in the outskirts, no matter what T cool by TSS is. So I'll get to the conclusions. Firstly, we started with the semi-cosmological setup, which we are trying to put up in some multidimensional simulations, where essentially we are not losing any physics of the cosmological accretion of gas, but we do not have mergers, and it's faster compared to a standard n-body plus hydro. Abundance matching technique gives us, even in a simple Lagrangian setup, abundance matching technique gives us a more or less realistic estimates of how much variance are thrown out and what kind of feedback power is required for each halo as a function of halo mass. We are trying to extend this thermal instability model to explain the reservoir of cold gas in the outskirts, in particularly lower mass halos. Eventually, we will try to put some realistic feedback, the kind of jets that BFF has in our group. So these are basically triggered by cold gas accretion into the black hole. So we want to put some more realistic star formation and feedback processes in our semi-cosmological setup. Thank you.
The energies from feedback is really high.
So, Yes. So one thing is that this is really the some kind of estimate of a very simple model. We do not have multi-dimensions. We just have concentric shells, and I think these picks will be a bit smoother with multi-dimensions. So, yeah.
So, so why? So you're suggesting that the CGM has a shallow entropy profile, that's why it's easy to condense gas.
CGM also has lower milieu temperatures, so I think in the ICM, if there is cold more rapidly, too easily it makes also in the outskirts. So CGM doesn't have a lot very high milieu temperatures, so a lot of cold clouds that enters as cold in the region. So that can provide a large gas and can explain some of the large amount of gas dissolved.
I have a technical question about how you implement density perturbations in your computations and analysis. I would say that what you're actually doing is putting a piece of our picture.
Right. Yeah. Right now it's icebergs.
That was my technical question.
Okay, answering the question. Let's start.